Good morning. Today we discuss the carrier transport phenomena. One of the carrier transport phenomena is the carrier drift. We know that there are various transport phenomena in semiconductor devices. The transport phenomena include drift, diffusion, recombination, generation, thermionic emission, tunneling, and impact ionization. The motion of these charge carriers, that is the electrons and holes in semiconductors, under the influence of an electric field and a carrier concentration gradient. So, we first of all, in the heading of carrier drift, we discuss the mobility. What is meant by the mobility of charge carriers? If we consider an N-type semiconductor sample with uniform donor concentration in thermal equilibrium, the conduction electrons in semiconductor conduction band are essentially free particles since they are not associated with any particular lattice or donor site. The influence of crystal lattices is incorporated in the effective mass of conduction electrons, which differs somewhat from the mass of the free electrons. Under thermal equilibrium, the average thermal energy of conduction electrons can be obtained from the theorem of equipartition of energy. Half kT units of energy per degree of freedom, where K is the Boltzmann's constant, T is the absolute temperature. The electrons in semiconductors have 3 degrees of freedom. They can move about in 3-dimensional space. Therefore, the kinetic energy of the electrons is given by half Mn Vth whole square, that is equal to 3 by 2 kT. Mn is the effective mass of electrons and V thermal is the average thermal energy. At room temperature, that is at around 300 Kelvin, the thermal velocity of electrons is about 10 to the power 7 centimeter per second for silicon and gallium arsenide. The electrons in semiconductors are therefore moving rapidly in all directions. The thermal motion of an individual electron may be visualized as a succession of random scattering from collisions with lattice atoms, impurity atoms, and other scattering centers. The random motion of electrons leads to a zero net displacement of an electron over sufficiently long period of time. The average distance between collisions is called the mean free path. The average time between collisions is called the mean free time, that is given by tau c. The typical value of 10 to the power of minus 5 centimeter for mean free path tau c is about 1 picosecond, that is of the order of 10 to the power of minus 12 seconds. When a small electric field is applied to the semiconductor sample, each electron will experience a force of minus q E if E is the applied electric field from the field, and will be accelerated along the field in the opposite direction to the field during the time between the collisions. Therefore, an additional velocity component will be superimposed upon the thermal motion of the electrons. The additional component is called drift velocity. The combined displacement of an electron due to the random thermal motion and the drift component is given as the net displacement of the electron in the opposite direction of the applied field. We obtain the drift velocity Vn by equating the momentum, that is force into time, applied to an electron during free flight between collisions to the momentum gained by the electron in the same period. The equality is valid because in a steady state all momentum gained between collisions is lost to the lattice in the collision. The momentum applied to an electron is given by minus q E tau c, and the momentum gained is given by Mn Vn. We have so q E tau c is equal to M E Ve. So Ve can be given as minus q tau c divided by M E E, capital E, that is the electric field. So it states that the electron drift velocity is proportional to the applied electric field. The proportionality factor depends upon the mean free time and the effective mass. The proportionality factor is called the electron mobility μn, and the units are centimeter square per volt second, or μn is given by q tau c by m e. Mobility is an important parameter for carrier transport because it describes how strongly the motion of an electron is influenced by an applied electric field. A similar expression can be written for holes in the valence band. So we have VE is equal to minus mu E, where E, capital E or E is the applied electric field, and similarly VH can be written as mu H E, where E is the applied electric field. The mobility is related directly to the mean free path between the collisions, which is in turn determined by various scattering mechanisms. The two most important mechanisms are lattice scattering and impurity scattering. The lattice scattering results from thermal vibrations of the lattice atoms in any temperature above absolute zero. These vibrations disturb the lattice periodic potential and allow energy to be transferred between the carriers and the lattice. Since lattice vibrations increases with increasing temperature, lattice scattering becomes dominant at high temperature. Since the mobility decreases with increasing temperature, the theoretical analysis shows that the mobility due to lattice scattering mu L will decrease in proportion to T to the power of minus 3/2. The impurity scattering results when a charge carrier travels past an ionized dopant impurity, that is the donor or acceptor. The charge carrier path will be deflected owing to Coulomb force interaction. The probability of impurity scattering depends on the total concentration of ionized impurities, that is the sum of the concentration of negatively and positively charged ions. However, unlike lattice scattering, impurity scattering becomes less significant at higher temperatures. At higher temperatures, the scattering moves faster. They remain near the impurity atoms for a shorter time and therefore they are less effectively scattered. The mobility due to impurity scattering mu L can be theoretically shown to vary as T to the power 3/2 divided by Nt, where Nt is the total impurity concentration. The probability of a collision taking place in unit time 1 by tau c is the sum of the probabilities of collisions due to various scattering mechanisms. We can say that 1 by tau c is equal to 1 by tau c lattice plus 1 by tau c purity, and so the mobility can be given by 1 by mu is equal to 1 by mu L plus 1 by mu S. The measured electron mobility as a function of temperature for silicon with 5 different donor concentrations is shown in the diagram. The theoretical temperature dependence of mobility due to both lattice and impurity scatterings. For lightly doped samples, that is sample with doping of 10 power 14 per centimeter cube, the lattice scattering dominates and the impurity scattering is most pronounced at low temperatures. The mobility increases as the temperature increases, as can be seen for a sample with doping of 10 to the power of 19 per centimeter cube. For a given temperature, the mobility decreases with increasing impurity concentration because of enhanced impurity scatterings. The measured mobilities in silicon and gallium arsenide as a function of impurity concentration at room temperature. The mobility reaches a maximum value at low impurity concentrations. This corresponds to the lattice scattering limitations. Both electron and hole mobilities decrease with increasing impurity concentration and eventually approach a minimum value of high concentration. Also, the mobility of electrons is greater than that of holes. Greater electron mobility is due to mainly to the smaller effective mass of electrons. And this is all. The mobilities and diffusivities of silicon and gallium arsenide as a function of impurity concentration has also been shown over here. And this is all that we have to discuss today. Thank you.